All right, thank you for your patience and thank you for joining us on our third series of technical sessions, where today is going to be about the passionate about cuttings. It's going to be introduced and presented by Mr. Mario. First of all, I would like to introduce Mr. Mario to the audience, and allow me for that. Mr. Mario is a highly accomplished professional with a proven track record of pushing the boundaries of science and technology, who holds a master's degree in electronic engineering. He joined the oil and gas industry in 2015 as a geolog data engineer, and swiftly moved to geolog R&D department as inorganic geochemistry specialist, mainly focusing on development and improvement of X-rays techniques for mineralogical and elemental analysis of rocks. Today, Mr. Mario is part of the data science team in geolog technologies, working on rock characterization methodologies and computer vision projects. Before we give the floor to Mr. Mario, I would like to hint some points about today's session. The session will be recorded and will be presented in our EAGE platforms. And in case if you have any questions, we will have a 5 or 10 minutes, let's say, Q&A at the end of the presentation. Feel free to ask at the end of the presentation. So, Mr. Mario, the floor is yours.
Okay, thanks for the kind introduction, and good afternoon, everybody. In case, good morning, good evening if you are in different time zone. And regarding questions, yes, please also take note of the slide number if relevant. Okay, so today, as I've been introduced, we will talk about cuttings, drill cuttings, and why we are passionate about cuttings, all a series of measurement of analysis of data that we can take out of cuttings. So first of all, why cuttings? Cuttings are a valuable source of information, not only a waste product, because in Geolog, as a surface logging company, we take care, our mission is to analyze everything that comes back or is available at surface. And so mud rheology, mud gas, and drill cuttings. Drill cuttings are an incredible source of information, a very valuable source of information. Also because nowadays cores are become less and less frequent, and cuttings are the only geological source of information that we have. That's why we are very passionate about what we can do with cuttings. The advantages of quantitative results available at the drilling sites are many. For example, you have a short lead times for analysis because you don't have to ship samples to the lab. So this means that you can have results in a matter of minutes, hours, and not weeks. You can collect extra samples based on results. So if you see some drilling breaks, some events, some very hard formation, you encounter something that you were not expecting, or you see results from previous samples, so you can collect extra samples and further investigate. You can optimize your budget because you can help the well completion before in quasi real time. So while you are there, you can help in optimization. You don't have storage issues because the cuttings are there. And most of all, sometimes you have to export cuttings abroad, and in many countries this is not possible. So you have no difficulties with sample exportation because we bring the instruments on field, we bring the measurements on field. This is made possible thanks to the new technologies, steep advancement in technology that is going faster and faster every year. So we have more robust instruments, less demanding in terms of operator experience, very simple to use, very robust, that can be deployed everywhere. And this is a trend that actually is not only in the oil and gas field, but in all scientific fields, we see this trend of bringing the lab to the field. And this is also a trend that is suitable to adapt with different types from collection, so with the fresh and the legacy cuttings, with the well type, mud type, bit type, so we have instruments that adapt to every kind of application. Today, I will show some applications. It's a very nice panoramic of most of the things you can do with the cuttings. And we will see first inorganic geochemistry applications such as assessing the rock matrix, lithotypes and stratigraphy, diagenesis in fracture proxies, anoxic proxies from the elemental data. Then we'll see gamma ray radioactivity measurement. Then residual gas, which can be hydrocarbons and non-hydrocarbons, and H2S detection. and also organic geochemistry for quantifying the organic content, the oil quality, and parameters like the biodegradation, the maturity. You will hear or read the name of some of our services. So to be more clear, what you will see is for lithotyping application, you will hear about digital cuttings, which is the combination of high-resolution imaging of the cuttings with artificial intelligence image processing to extract data from the pictures. Then for rock matrix, you will hear about GeoRocks, which is the combination of X-ray fluorescence for elemental data and X-ray diffraction for mineralogical analysis. And this is to detect the different minerals as well as porosity, fracture, and anoxic environment indicators. Then we will see an application of residual gas, so the measurement of residual occupied pore space in cuttings as an indicator of qualitative permeability. And you will also see that this is pretty intuitive, our GeoGamma, which is a natural gamma ray analyzer for the inorganic. Then we will go also in the organic. So digital cuttings, as I was saying, is the combination of high resolution imaging, so 24 megapixels of the washed and dried picture, very nice picture that you see on the bottom left, high detailed, and under UV light for detecting the fluorescence, so fluorescent minerals and oil shows. And from these pictures, we can actually extract data, so color extraction, different parameters of the color in the color space, and particle segmentation. So you have also the particle size distribution of the sample, and this can help with the grain size to understand the type of lithologies. And this is as the ultimate goal of basically finding lithotypes or lithoschemes. And for these, you can integrate data like gamma ray or computed gamma ray from elemental data. You can integrate the elemental data and ratios from fluorescence or other technologies, mineral data, everything that you can also measure, you can integrate. And you can combine with the brightness, with the color space data to cluster the data into the different lithotypes, which have a very similar composition, very similar characteristics. Another application, many applications that you will see under the GeoRocks, so the combination of X-ray fluorescence for elemental data and XRD for mineralogical data, you will see after this. And here we have the combination of X-ray fluorescence technique, which gives data for 32 elements, 10 major elements like silicon, aluminum, calcium, magnesium, and so on, reported as oxides in weight %, and 22 elements reported in parts per million, and relevant chemostratigraphy ratios and markers for porosity, fractures, we will see, combined with X-ray diffraction to identify different mineral species, clays included, clay speciation included, and this is to create mineralogical and elemental logs that are able to distinguish different, also here, the different stratigraphies. Some examples, for example, we have here in carbonates, we can use elemental data as a porosity indication, because in carbonates, the diagenetic degree is, during the diagenesis, there is an abundance of certain elements. So manganese, iron, and zinc tend to accumulate with the diagenesis. So you expect to have an inverse correlation with the total gas. And this is really self-explaining in this graph. So you expect when you have higher strontium, sodium, and magnesium, statistically to have higher porosity, so higher gas from mud. And while you have higher diagenesis, you see these markers like manganese, iron, and zinc, very abundant, and you expect to have lower porosity. You can also find markers for fractures, again in carbonates during hydrothermal alterations. You can have deposits of certain mineral species in very small amount, so probably you cannot detect the mineral species, but you can detect the trace of these minerals. And these minerals usually contain heavy elements like zinc, sulfur, lead, arsenic, nickel. So when you have anomalies of these elements in carbonates, they are usually proxies of fractures, usually cemented fractures. And this is a very important information, especially when you want to produce through fracture and not through direct permeability. Then we can switch to a residual gas, as even if residual gas is actually as a technology for assessing hydrocarbon and non-hydrocarbon gases. Here we see an example to assess the rock matrix, to assess the rock permeability and the gas storage capability of the rock. To understand how this service works, we compare the extracted gas from mud, so the mud gas, we compare with the headspace. In the headspace, we have a desorbed gas that develops in the free space in this sealed vessel. And then we also grind the cuttings and we measure the residual gas that is not extracted from the pores. This is widely used in unconventional. So, for example, in the Barnett Shale, which has a very low porosity and low permeability, the common behavior is the Barnett Shale will release around 40% of the gas in the mud gas, and another 20% will be desorbed in the headspace, but another remaining part, 40%, will stay in the pores because of the low permeability. How can we use this? We have, for example, this case. We have carbonates. We found a high extracted gas, so in the range of 10,000 ppm in the mud gas. And then we analyze the headspace and the residual gas in the pores. And we see that we have a low desorbed gas in the headspace, 1,000. Okay, it's not very low, but it's tenfold lower than the mud gas. And basically negligible residual gas in the pores. What is the outcome of this is that we have a high rock permeability because all the gas is released in the mud gas and in the headspace, and very, very low amount stays in the rock. So the rock has a very low storage capability. We also have a natural radioactivity measurement tool, which is called GeoGamma. This basically measures the direct radioactivity from uranium, thorium, and potassium. And this, of course, as you may be familiar also with the downhole tools, is helping in understanding the different lithologies, in particular the presence of shale versus sandstone carbonates. We have an example here of the direct measurement of radioactivity compared with the elemental data computed gamma ray from XRF in this case. And this has several applications. One, for example, can be used for cutting allocation. If you have, for example, highly deviated well, very long horizontal well, you can compare with the downhole gamma ray to be sure that the cuttings are coming where you expect they are coming with the lagged depth. Or in simpler case, when you have vertical wells, you are not worried about the cutting allocation, you can even avoid downhole gamma tools. If we move to organic geochemistry for fluid characterization, we will see mainly two names. One is geosource, so for source rock characterization, which is the combination of total organic carbon measurements with the pyrolysis, which is the equivalent of rock eval or source rock analyzer, you may be heard. And G9+, which is a technique for thermal desorption of liquid hydrocarbons that measures species from with more than 9 carbon elements, so C9 to C35. And this is used for oil quality assessment, depositional environment, maturity and biodegradation, identification of bitumens, paraffinicity of the oils, and so on. So we start with the geosource, as I was saying, is a combination of the total organic carbon with the pyrograms that you see here on the left, which are composed of usually two peaks. The S1 peaks is the free hydrocarbons remaining in the rocks, and the S2 instead that develops at higher temperature is the residual petroleum potential. And these pyrogram and the total organic carbon give an important indication of the kerogen type and the maturity, the kinetic of hydrocarbon cell generation, and other outcomes that we will see. So the source rock properties that we can measure are the first four: total organic carbon in percentage, the free hydrocarbons in the rock expressed as milligram per gram of rock, the residual petroleum potential, again milligrams per gram of rock, and the temperature at maximum generation of the S2 peak. And with these four parameters, we can calculate the hydrogen index and the production index, which give an idea of the kerogen type and other characteristics. Some examples: we want to investigate unconventional reservoirs to understand the organic content and maturity, and in view of producing by hydraulic fracturing stimulation. So first, we see high TOC values all along the well, higher than 6%, with peaks around even 12%, so very high organic carbon content. And this is also inversely directly related, directly proportional to uranium, which is an anoxic proxy by the XRF, by elemental analysis. And we also add the pyrogram data, in this case, the residual hydrocarbon potential, so the S2 peak. And we plot the S2 against the TOC in this kerogen quality plot, and we see that all data points fall in a high hydrogen index region, which indicates a type 2 oil prone, usually marine. So we can assess the kerogen type, and we know that it's a good quality type 2 kerogen. We can use geosource also for bitumen identification. So here, for example, the challenge is that we have a presence of bitumen in certain layers of the reservoir that significantly reduce the producibility because it blocks the flow, the pathways, so it makes more viscous. So, and they are quite difficult to identify. So we see that the permeability drastically drop with the increase of bitumen saturation, as you see in the graph on the right. So we can apply the TOC, the geosource of TOC and pyrogram, pyrolysis measurement. And we see that in all the first interval, we have a good free hydrocarbons, S1 peak. And then it drastically decreases in the lower part with the appearance of residual hydrocarbon potential, but with very low values, which are not interesting from a producibility point of view. So this is a marker for bitumen, high organic content, low producibility. So the bitumen is detected and quantified, and these can be excluded from production because can give problems during the production. We will see another application in which we combine organic and inorganic geochemistry. Here we have a challenge because we have difficult lithological interpretation. This is mainly due to the PDC bits and the presence of alternation of silty shale together with the sandy layers. And these sandy layers were rich in potassium, so also the gamma ray was not really diagnostic of the stratigraphy. While if we combine data from elemental markers and the TOC, we are able to distinguish in this stratigraphy actually three different regions. The top and the bottom part are two reservoirs with much more abundance of silicon over aluminum, which is a marker for sandstones versus clays. And also the presence of higher TOC and higher uranium proxies and molybdenum, which are anoxic proxies that can help us to detect the source rock in the middle. So the result is that by using more advanced measurements than the only geological observation, these helped us to identify different layers of shale with interbedded sandstones, and these also contribute to well zonation and well completion. Another example is using the same source of data for real-time geosteering. So the target here is to keep the well in trajectory, trying to stay in anoxic layers for future fracking. And we can see from the data that we are able to distinguish also here by using TOC as a marker for organic matter, and the same for phosphorus, which is a paleoproductivity proxy. Together with anoxic markers, in this case, the formation was rich in molybdenum. and also lithology, of course, lithology markers such as aluminum and calcium, which are directly related to clays and carbonates. And this helped us in identifying the two better regions for fracting, so rich in organic matter and paleoproductivity proxy, which are, of course, the two carbonates. Now we will move to oil quality assessment, and here we will see the thermal extraction gas chromatography. And this provides a very rapid quantitative and simultaneous determination of species which are higher than C9, so from C10 to C35. And this is a very nice fingerprint of the oil that is present in the formation and in the cuttings. And this information from this chromatogram, we can get early information and real-time information in just 10 minutes, as you can see, about the fluid type, quality variations, fluid contacts, maturity and biodegradation occurrence, and so on. Some examples, we know from literature, and it's well known that during the biodegradation, the normal chain hydrocarbons, or the normal, in this case, for example, normal C17 and normal C18, will be consumed first compared to the more complex hydrocarbons, so chained hydrocarbons and multiple loops hydrocarbons, like pristine and phytane. And we can use this ratio because pristine and phytane are quite abundant, also compared to C17 and C18. And if we use the ratio between more complex molecules, like pristine over normal C17 and phytane, ratio phytane to normal C18, we can understand if biodegradation is happening, because we expect that with biodegradation, phytane and pristine will become more abundant. So the biodegradation will move in the top right of the diagram in the right. And also the type of depositional environment, if we have an oxidizing or reducing environment, will appear also in this plot. So this will be an indication of maturity, biodegradation, and depositional environment. We can use the biodegradation markers, for example, in this case. We have our challenge here is that the oil production showed a steep decline when the water cut increased, so close to the oil-water contact, the oil was getting more viscous. And so the problem is that with high oil viscosity and poor mobility ratio, the problem here is that with the downhole sampling couldn't be done in all wells and in many different points because of time and cost reasons. So we can apply this very simple measurement at the field using, again, the same markers. In particular, in this case, we will use phytane over C18. And we see that when we get close to the transition zone, this ratio highly increase, showing biodegradation. Of course, biodegradation occurs because close to the oil-water contact, you start having bacteria, so the biodegradation occurs, and your viscosity increase, and your production decrease. So getting a sort of threshold on this phytane over 18, we can stay away from the high viscous zone and optimize the production. So the biodegradation is confirmed through this ratio, and this can help to the well completion and development. By using the chromatogram here in the slow mode, in order to have higher resolution, you can use the alpha slope, which is the slope of the maximum height of all the peaks. The alpha slope is used for oil quality assessment. There are also ways to qualitatively assess the IP gravity of the oil. It's better if it's calibrated field by field. There is literature on this. And so you can use the alpha slope. The more is the slope, the lighter hydrocarbons you have. And here another example, how you can assess oil quality, because as I was saying, the chromatogram in a certain region is like a fingerprint of the oil which is present. And you can distinguish different types of oil. On the left, you will see a paraffinic oil, which is richer in heavier components against a non-paraffinic oil, and also NaOCO-rich oils, so oils which are rich in nitrogen, sulfur, and oxygen. You can assess by using this technology. as well as also developing a different pyrolysis ramp, focusing on more temperature ranges. You can further divide the S1, and instead of having the S2 peak, you have different regions where you focus on different lighter and heavier hydrocarbons generation. So you can use this technology to assess and distinguish different types of fluids, different types of oil. We move to non-hydrocarbon detections. Again, we use residual gas. So this is very useful to assess the H2S. While nowadays, most of the mud systems are equipped for safety reason with H2S scavengers, which of course makes everything easier. The problem with this is that we have no direct assessment of the H2S that is present or not in the cuttings, unless you do fluid sampling. So the scavengers are very useful during drilling, but you lose relevant information. We can assess this information by analyzing the cuttings. So we can grind the cuttings and measure the residual hydrocarbons inside the pores and detect H2S. This, of course, is very, very helpful because you can help in well completion, in the pipes material selection, because you may not see any H2S because of scavengers, but if H2S is present and you don't correctly plan your completion, H2S, you know, is deadly, but it's also highly corrosive, so your well completion could be a problem. Also, you can select downhole sampling. Instead of sampling multiple times, you can select based on residual gas results. So you can confine your downhole sampling points to certain layers where you expect to have H2S. And also safety, of course, because you may not see by the scavengers, but the cuttings can be still releasing H2S when they reach surface. So to recap, we have seen a very wide panoramic ranging from organic to inorganic geochemistry, made possible by recent technologies that have been brought, very advanced technologies that have become robust and portable to be brought on the field. So you can do these technology, you can apply these technologies in real time at site for high resolution imaging, elemental and mineral analysis, gamma ray measurement, residual gas assessment, so hydrocarbons and non-hydrocarbon, source rock analysis, oil chromatography, desorption, and pyrolysis, to assess quasi-real-time data and help in completion by having lithotyping, fractures, and porosity and permeability assessment, layers identification, H2S assessment, organic content and maturity assessment, identification of bitumens, biodegradation, oil quality, paraffinicity, for an integrated formation characterization. Thanks for your attention. If you have questions, feel free.
Thank you for the interesting presentation, Mr. Mario. And thanks everyone for listening to the presentation. Now it's floor for Q&A. If you have any questions, please feel free to ask, either by raising a hand or sending a message in the chat. So I think I will kickstart these questions. Mr. Mario, I would like to ask about the geo walks. What is the minimum sample size? And in terms of analysis time, since it's an on-site, let's say, surface, so what is the analysis time between getting the XRF and XRD data?
Okay, so usually the sample size that we use is we need around 2 grams of sample, washed and dried sample for XRF, and a very small amount, around 100 milligrams for XRD. So it's a very low amount of sample because 2 grams is very easy to collect. Usually when you talk about unwashed, you keep saying more than 5 grams just to be sure for repeatability and everything. The measurement is pretty fast. Is still a statistical measurement, so ideally the longer you measure, the better are the results. But nowadays, with the current technologies, a 10-minute analysis will be very repeatable and very precise. So these are very, very fast techniques. 10 minutes, you can get 32 elements. With this type of XRF, you can have different types of XRF. And the same 10 minutes for XRD acquisition plus a few minutes for interpretation. So very fast techniques that can be applied in quasi real time.
Okay. And another question, is it possible to differentiate between bitumen and pyrobitumen in cutting sample?
This is, I have to admit, I'm not really an expert of the organic geochemistry. So I have to admit, I'm not really sure about.
Thank you. Any other questions?
I'm available to come back on this if you make an inquiry,
Sure.
talking with the organic geochemistry experts, because I'm a little bit out of my field on this part. So
So still any more questions? There is one other question here by Ms. Shama. She said, how can you minimize the contamination in the sample?
okay, the contamination, I mean, you're probably talking about mud contamination. So when we talk about inorganic geochemistry, this is really not that relevant as long as we have very strict cutting washing procedures that help in removing all the mud additives. Of course, some of them will stay. So, for example, you still have some residuals of barium, of chlorine, depending on the mud additives regarding the inorganic geochemistry. For the organic geochemistry, it really depends because also here, of course, we wash the sample in a very systematic way using SOX-tech, so with using solvents that remove the mud contamination from the outside, preserving the organic content inside the rock. But some mud contamination can still persist. And for some application, it may be useful to have mud as a reference because the signal of the mud, the oil composition of the mud, especially if it's oil-based mud, can be used to fine-tune the results of the organic geochemistry. But usually the sample washing procedure are quite strict, quite precise, that the mud contamination is made almost negligible or negligible at all.
We have another question here from Taiba. In case of deep soil stroke and it's requiring oil-based mud, does that will affect the results of the TOC assessment, and how to quality check that?
Okay, also this one is strictly related to the previous question. It's again a matter of basically contamination of the sample. So we have seen cases in which removing the mud contamination has been harder, but this can be solved by using different type of solvents. So the polarity of the solvent is really relevant in removing certain types of oil-based mud or additives. And in case we found contamination, we can assess contamination actually but also by looking at the pyrogram, because it will not be so clean. So you can measure the TOC and you detect that there will be a mud contamination. So it's a matter of rewashing the sample with a different solvent, with a different polarity, understanding what type of contamination we have. So we have a standard routine for washing, but sometimes the polarity of the mud makes the mud persistence, and we need to change the solvent for that. But it's rare cases, and all of them can be assessed.
Okay, I guess we reached the end of this session. Thank you, Mr. Mario, and thank you everyone for joining us. And please also be informed that we're not finished yet. We have an upcoming sessions in the upcoming months. So stay tuned. We'll shortly send all the invitations and all the advertisement about that. And this presentation and or session is recorded and will be shortly also will be viewed in our platforms. So thank you very much and wish you all the best.
Thank you very much.
Thank you.
Thank you all.
Thank you all.
Thank you. Thank you.
Thank you, Mario.
Thank you.